Hello everyone, and welcome to today's class. So we are continuing on hypothesis testing, and last week we looked at hypothesis testing for the population mean using one sample, and we started by saying that if we choose a sample, so we're just recapping, so you may not need to note a lot of things. If we choose a sample of size n from a normally distributed population whose parameter, which is defined by this, from a normal population like that, then the hypothesis of interest would be H naught, that mu is equal to mu naught, where mu naught is some hypothetical population mean, which will always be given. In an exam setting, that value will always be given. So you can test this against H1, which says either mu is less than mu naught, or H1 that mu is greater than mu naught, or H1 that mu is different from mu naught, where the first scenario here, these are lower tail test, is an upper tail test, and these are two tail tests. Okay, so when testing this kind of hypothesis, there are two scenarios. Number one is sigma is either known or unknown. So if sigma is known, you use the standard normal or Z statistic. So Z is equal to X bar minus mu naught divided by sigma over root n, where the divisor here, this is what we are calling the standard error of the mean, which sometimes we denote as standard error of X bar like that. Okay, so when sigma is known, you use the standard normal as the statistic. Okay, then there are times when sigma is unknown. When sigma is unknown, number one, you estimate sigma using S. So you estimate the standard deviation of the population using the sample standard deviation. And then in this case, you use a T statistic. So please note the difference that when sigma is known, by default, you use Z. But when sigma is unknown, first you estimate it using S, and then you use the T statistic, which has the same formula, just like the Z, divide by that. But now here you have S instead of sigma over root n. Again, where this divisor here is the standard error of the mean. So that is standard error of X bar. But we noted that if n is large, the T distribution is approximately equal to the normal distribution. So you can use the Z statistic if you are working with a large sample. So if the sample is large, you can just use the Z statistic. Okay, so the T statistic is mainly used. So T is only used when n is small. But of course, when normality is assumed, when normality of the population assumed. Okay, so that's what we looked at last week. We did one example using the Z statistic, and then I gave you an exercise. That you have to do at home about rainfall. So maybe I can share with you the question. So this is a question that I gave you to look at home. I hope you have looked at it. So let's try to go through this question very fast. So we'll need several things. Solution, so we can say that solution. So you notice that in that question, you are given n is equal to 10. Then you are given the hypothetical population mean as 22. Sigma is not known or is not given as per that question. Then using the available data, you can obtain X bar, which is given by summation of X divided by N, which is 25.87. And then S, which is the standard deviation. So I think we need a square root here. So here we have a square root like this. We have square roots there. Okay, so the answer is 4.751152. We have obtained the answers in R in the background. Huh? So using this information, we need to test the hypothesis. The null hypothesis is that always mu is equal to mu naught. Mu is equal to mu naught, and our mu naught is 22. Then H1 will be mu, and then we have a 22 here. Then from the question that we are trying to answer, we should know whether we are going to use a lower tail test, an upper tail test, or a two-tail test. So let's go back to the question and see what is required of us. So the question here is, scientists at the weather station wish to test whether the average annual rainfall has increased from its former value, which is 22 centimeters. So we're testing the hypothesis that the mean annual rainfall has actually increased from 22. So this is calling for an upper tail test. So this is calling for an upper tail test like that. So we can even set up our critical region at this point. So our alpha will be on this side. So this is our alpha, and we're assuming 5%. So if that is our alpha 5%, we need to get our Z. Here we're going to use T critical. So we need T critical here. T critical in this case, because we are working with a small sample. So our T statistic, which I'm going to call T calc to avoid confusion, will be given by X bar minus mu naught over S over root N. And our X bar is 25.87 minus our mu naught is 22 divided by our sigma, our S is 4.75 etc. divided by root, like that. So the calculated T statistic is 2.576. Then we need to obtain the critical T statistic. And for us to obtain that, we need to know the degrees of freedom. In our case, it will be 10 minus 1, which is 9. Then we also need to know the level of significance. In our case, we're using the default level of significance, which is 5%. Then we also need to know that it's an upper tail test. So we need to get that value there. So let me share with you the T tables. So these are the T tables. And this row here, the upper row, this row here indicates the different alpha, levels of alpha that you can use. So in our case, we're using 5%. And it's one tail test. These tables will give you the upper tail test, but you can always map them on the lower tail test using the concept of symmetry. Then 9 degrees of freedom, 9 degrees of freedom here. So the T critical value will be this number here, 1.833. So this will be 1.833. So once you have that, once you have the critical value and the calculated value, now you need to make your decision. So you need to say whether the calculated value falls in the acceptance region or in the rejection region. And we notice that our value is lying deep in the rejection region. So we notice that the T calculated, which is 2.576, falls in the rejection region. It falls in the rejection region. And that tells us what we are going to do with the null hypothesis. So hence, we reject the null hypothesis. Hence, we reject the null hypothesis. The null hypothesis, that is H naught, that mu is 22 in favor of, we reject that hypothesis in favor of the H1, which is saying that mu is bigger than 22 at the 5% level of significance. At the 5% level of significance. So we can say now the conclusion is that there is reasonable evidence, or we can say that it is reasonable to conclude, that the long-term rainfall, mean rainfall has increased from its former value, So the last bit here, or this last question here, the last statement here, sorry, is the answer to the question. This is the answer to the question. Okay, so basically that's what we looked at last week. So that was part of the exercise. I hope everyone is comfortable with it. Now I want us to move to the next type of hypothesis to be tested here, and this is about the variance. So our next subtopic is testing the value of a population variance. So let's have some introduction by saying that consider a random sample of size n. Consider a random sample of size n from a normally distributed population with mean mu and variance sigma squared, with sample variance given by s squared, and we are testing the hypothesis, So our null hypothesis here is that sigma squared is equal to sigma naught squared, where sigma squared is of course the population variance, which is always a known. Then sigma naught squared is the hypothetical population variance, which will always be given. Okay. Then the test statistic in this context, will be chi-square given by n minus 1. Then you have this ratio here of s squared divided by sigma naught squared. Okay. So we have that statistic, of course, where the degrees of freedom will be n minus 1. Then we note that for large samples, and this is anchored on the central limit theorem, for large samples, the test works well. Even if the population is not normally distributed. Okay, so let's have some example. This should be our example number 8. Example number 8. So this is the example. You are told to carry out a statistical test to assess whether the standard deviation of the heights of 10-year-old children is 3 centimeters based on the random sample of 5 heights in centimeters given below. Assume the heights are normally distributed. So this assumption is very important. Assume the heights are normally distributed. And these are the 5 heights: 124, 122, 130, 125, 132. Okay. So remember, we need to test this hypothesis. Here. And the test statistic will be given by that. So for us to obtain the test statistic or the calculated statistic, we need the value of s squared, which is the sample variance. And the sample variance can be obtained using this formula here. S squared is equal to summation of x squared minus n multiplied by x bar squared divided by n minus 1. For small samples, the divisor is always n minus 1. Then when you work it out using that formula, you'll obtain that your S squared is 17.8. 17.8. So now let's define the hypothesis that we need to test here. So the hypothesis to be tested here is H naught. We are testing the hypothesis that H naught, that sigma, remember this is S squared. Yeah, so we're given S in the question. So this is 3. This is 3. So we're testing this versus H1 that sigma is, what's the question? Carry out a test to assess whether the standard deviation of the heights of 10-year-old children is 3 centimeters. So it's either 3 centimeters or it's not 3 centimeters. So this calls for a two-tailed test. This is a two-tailed test, okay, based on the chi-square distribution. So the chi-square calculated value will be given by n minus 1. Then here we have S squared divided by sigma naught squared, divided by sigma naught squared, where our n is 5, so this will be 4 times, here we have 17.8 divided by sigma naught squared, which is so our sigma naught is 3. So that means that our sigma naught squared is 9. So here we shall have divided by 9. So let's work out this value and get the statistic, the calculated statistic. So the calculated statistic will be 7.91. 7.91. So let's illustrate the critical region. Remember here we're going to be using a chi-square distribution. So we're going to have a distribution that looks like that. And it's two-tailed test. So this is where you have your alpha. So this will be your alpha over 2, which is 2.5%. And here you have the other alpha over 2, which is 2.5%. So I want us to use the tables. So this usually this starts from 0. I want us to use the tables to obtain the critical values. The degrees of freedom will be equal to 5 minus, what did I say here? Yeah, the degrees of freedom will be 4 in our case. Degrees of freedom will be 4 in our case. So our chi-square distribution tables are here. They are here. So the upper tail of that distribution is what will be given by chi-square alpha over 2. So this is this value here. Alpha over 2 is this value there. Okay, and the lower value will be given by chi-square 1 minus alpha over 2. So I hope you will be able to notice that difference. That on the lower tail, we are getting the critical value from this number here. 1 minus alpha over 2. So this is the upper tail, and then the lower tail will be this one, will be given by this one. This is the lower tail. Okay, then we are working with 4 degrees of freedom. So the values must be along that line. Huh? So the upper value will be 11.143, and the lower value will be 0.484. So let's put those values on our diagram here. So this is 11 point, we said 11.14, let's say 143. And then the lower value is
0.484.
Yeah, 484, thank you. So now, so this is the acceptance region, the unshaded part. Then the shaded part is your rejection region. So we need to locate this value, the calculated statistic, on this diagram, and clearly it will fall somewhere here, 7.91. It is in the acceptance region. It is in the acceptance region. So we say that chi-square cal, which is a 7.91, falls acceptance region. So hence, what do we do to the null hypothesis? Hence, we fail to reject the null hypothesis, that is H naught that sigma is equal to 3 in favor of H1 that sigma is different from 3 at the 5% level of significance. We fail to reject. Usually we avoid using the word accept the null hypothesis. Huh? We fail to reject the null hypothesis in favor of the alternative at that level of significance. Okay, so that's basically how you perform that simple test. Any question there? Any question there? So we can also use the p-values method. You can also use the p-values method to decide whether to reject or fail to reject the null hypothesis. So I'll show you how to use the R code in this case. So the R code in this case will be for the upper tail. For the upper tail will be P chi-sq. Then we have 7.91, which is our observed test statistic. Then we have 4 degrees of freedom. Then usually you say lower dot tail is false. And now because these are two tail tests, you must always multiply here by 2. You must always multiply there by 2. So let's quickly go to R and do it very fast. We see the observed p-value. So you will tap the R code this way. And because these are two tail tests, you're going to have a ×2 here, because the first part of the code here will give you the probability on the upper side. Will give you 1/2 of the rejection region. So you multiply it by 2 to get the entire p-value, because these are two tail tests. And you notice that your p-value will be 0.189, something like that. Your p-value will be 0.18, let's say 0.19, which is larger than 0.05. So that means you cannot reject the null hypothesis. So let me resume the recording part. So when you type the R code, you will get that the p-value is 0.089, which is around 0.19. Then you notice that this value is larger than 0.05, which is our level of significance. So if the p-value is larger than the than the level of significance, you fail to reject the null hypothesis. And so we shall end up with the same conclusion as the one we observed using the tables. So the conclusion will be the same this way. So we have some exercise that we're going to look at, and the exercise is making the same assumptions as previously, as in the above example. Test at the 5% level of significance whether the standard deviation of the annual rainfall at the weather station in example 7 is equal to 4. You test whether the standard deviation is equal to 4. So you'll show me the workings later on. Okay, so if there's no question, let's move to our next subtopic, which is testing the value of a population proportion. Testing the value of a population proportion. So let's have this kind of introduction. Consider a general binomial experiment. Consider a general binomial experiment with n trials, and probability of success given by pi, and let sorry, this pi here is refers to the population, huh? And then we say that and let x be the number of success outcomes, testing the hypothesis that h naught, that pi is equal to some pi naught. That's analogous to this, mu is equal to some mu naught. It's analogous, so it's the same. It's only that now we're using different symbols because we're in a different distribution. Okay, then we say for large n, that is for large samples, and you notice that for this kind of approximation, we must always have a large sample, especially if you want to use the standard normal statistic. We always have to pick a large sample for if we are sampling from a binomial distribution or from a binomially distributed population. Okay, so for large n, we use the normal approximation. To the binomial. And of course here, with a continuity correction factor. Of 0.5. Or usually it's plus or minus 0.5. Okay, so that is, so if n is large, this is the test statistic that we use there. We say z is equal to p, but here you have to either add or minus 0.5 over n minus your pi naught divided by the square root of pi naught, 1 minus pi naught divided by n. So please notice that this part here, in the context, if you were just working with a continuous distribution, you would have it like that. But because we are estimating a discrete variable with a continuous variable, we are adding the continuity correction factor here. In this case, it will be plus or minus 0.5 over n. This formula is exactly equal to, if you use the number of successes x, and here you either say plus or minus 0.5, then here you have n multiplied by pi naught divided by square root of n, then you have pi naught, then 1 minus pi naught. So like that. So please notice how you add the correction factor when we're using p. I'm going to explain p, or the number of successes. So let me say that where n is the size of the sample, then pi naught is the hypothetical population proportion. Then P is the sample proportion. So it's good for you to note what is happening here with the correction factor when we're using the sample proportion and when we're using X, which is the number of successes. Maybe the second version is a little bit easier to work with. But if you work with the second one or the first one, the answer will always be the same. Actually, these are just two versions of the same formula. So let's note that when carrying out tests of this type, you can work out whether you need to add or subtract the half or the 0.5 in the continuity correction. If you remember that you always adjust the value of x, so you need to note that you always adjust the value of x. Towards the mean. The mean of the distribution under H naught. Okay, so that means that, for instance, if your p is 0.2 and your pi naught is 0.3, you need to adjust upwards. So you add like that. And on the other hand, if your p is 0.2 and then your pi naught is 0.1, you need to adjust downwards. So you should adjust in the direction of the mean, or you should adjust towards the mean of the distribution given under H naught. So here we'll have minus 0.05. And of course, when you're using p, we are dividing by n. Even here we'll be dividing by n. Okay, so we'll see that more practically. So example. This is our example number 9. So the example says that in a one-year mortality investigation, for 45 out of the 250 90-year-olds present at the start of the investigation died before the end of the year. Assuming that the number of deaths has a binomial distribution where n is equal to 250 in this case, and the probability of success is pi, test whether this result is consistent with a mortality rate of pi is equal to 0.2 for this age. So solution. So we are testing the hypothesis. We are testing the hypothesis that H naught, that pi is 0.2 versus H1. So we are testing whether this result is consistent with the mortality rate of pi is 0.2. So the alternative hypothesis should be different from 0.2, so which is calling for a two-tailed test. So we are also given, n, the number of trials is 250, and x, which is the number of successes, x, which is the number of successes in this case, which is a number of successes, is equal to 45. Is equal to 45. So with that information, and now we can obtain our z calculated, assuming normality, because n is large, so we can assume normality. So we can use any of this formula here. We can use the first one, where in the first case we need to obtain p. Then after that, after you get p, the rest will be easy to see. So let's work with the first formula there. So we're going to have p plus or minus 0.5 over n. So this is just like an item, pi naught divided by square root, then you have pi naught 1 minus pi naught divided by n. So p is the probability of success, which in this case will be 45 divided by 250, which will give us how much? 0.18. Okay, then the other information is given. So we shall have this is 0.18 plus 0.5 divided by n. Our n is 250. Then after that minus pi naught, and our pi naught is is the hypothetical value, which is 0.2, divided by the square root of 0.2 multiplied by 1 minus 0.2, which is 0.8, divided by 250. So that's our z calculated. So which gives a calculated z value of minus 0.7115. If you use the other formula, you should get the same answer. If you use the other formula, you should get the same answer. That is, if you use alternatively, if you use z is equal to, now you're using x, so you will have x is 45, 45 plus 0.5 minus, now you have to put n here, so this will be 250 times that divided by the square root of, I start with n, 250 times 0.2 times 0.8. So you can confirm that the answer is the same there. So you notice that the two formulae will give us the same answer. So just choose one of them. I think the second one is a little bit easier or straightforward. But you notice that whether you are adding 0.5 or you are subtracting 0.5 really doesn't matter when your n is small. Doesn't matter. But usually the rule is, as I explained a little bit earlier there. So what's the critical value? The critical value. So we are using the standard normal distribution, two-tailed test. Two-tailed test. So this is 0 there. So two-tailed test, is it? Two-tailed test. We are assuming alpha 5%. So the critical value will be 1.96 minus 1.96. So the critical value of z is plus and minus 1.96. Okay, so now let's see, where does it fall? The critical value is somewhere here, minus 0.7115. Remember, this diagram is not drawn to scale, but it's somewhere in the acceptance region. So we say that, we conclude that, we say that since the calculated statistic falls in the acceptance region, since the calculated statistic falls in the acceptance region, we fail to reject the null hypothesis in favor of the alternative, hypothesis at the 5% level of significance. So we cannot reject the null hypothesis. Hence, so this is our conclusion. Hence, it is reasonable to conclude that, the true mortality or mortality rate, the true mortality rate for the age, or for the age under consideration, is 0.2. So it is reasonable to conclude that the true mortality rate for the age under consideration is 0.2. That is the end of that particular question, that example. So the same conclusion can also be obtained using p-values. And we are looking for this probability. This being a two-tailed test, and our observed statistic is here 7,115. So we're looking for this area and also for an equal area on the upper side. So this is 0.7115. So we're looking for that area. So the R code there will be, so the R code will be, you have to multiply by 2, then you have P norm, and you have minus 0.7115. Alternatively, if you want to use the positive side, you can say 1 minus P norm, and you have 0.7115. But now you have to take this value here and multiply it by 2. Like that. So these two will give you the same answer. I think the first one is simpler, so you can use the first one. So when you run the R code, as you've done in the background, you notice that the P value, so the P value in this case is 0.47677745, which is extremely large, which is a very large P value. Large P value. So when the P value is large, it means that you cannot reject the null hypothesis. So you fail to reject the null hypothesis at the 5% level of significance. And that means we shall end up with the same conclusion. So you can either use the P value or you can use the table, the critical values obtained from the tables. Okay, any question there? Any question there? So we can have an exercise. So the question is, a new gene has been identified that makes carriers particularly susceptible to a particular degenerative disease. In a random sample of 250 adult males in a certain country, 8 were found to be carriers of the disease. Test whether the proportion of adult males born in this country carrying the gene is less than 10%. Okay, so you need to test that hypothesis. So solution, let me tell you what is given there. You are given pi naught. You are given pi naught. The hypothetical population proportion is 0.1, 10%. Okay, then you can always obtain P. So the number of, also the summation of X. So the number of successes is 8. So P, we can get 8 out of how many were sampled. Okay, and clearly your N is 250. So proceed from there. Then our X is 8. So that's what we have. So you can use the steps that we have shown in the previous example to answer that question. So our next topic is testing the value of the mean of the Poisson distribution. So let's have some introduction. Consider a random sample of size n, a random sample of size n from Poisson with a parameter given by lambda from the Poisson distribution. On the Poisson distribution, testing the hypothesis H naught that lambda is equal to lambda naught. And we say for large samples, a normal approximation can be used. So we are just saying that we can use the Z statistic. So for large, but when the samples are larger, for large samples, a normal approximation can be used for the distribution of the sample sum. The distribution of the sample sum. or sample mean. Sample sum or sample mean. We need to remind ourselves something here, that recall that if you take the summation of xi, this one has a Poisson distribution where the parameter or with mean is equal to n of that, which is approximately a normal distribution where mean is equal to n lambda and variance is n lambda. Remember, for the Poisson distribution, the mean is equal to the variance. So that's why the mean here is equal to the variance. So when you are switching from the Poisson to the normal, then the mean will also be equal to the variance. Then we can say that the test statistic, in this case, will be given by z is equal to, there are two options. You can have x bar, the sample mean, minus lambda naught, which is the hypothetical lambda, then divided by the square root of lambda naught over n, which is equivalent to, if you want to use the summation of the number of successes, summation of xi minus n lambda naught divided by the square root of n lambda naught. So please notice that the two formulae are just the same. Huh? This is just the same as this, because we know that x bar is given by summation of xi's divided by n. So if you want to use xi's, you can see at some point, that's why we are multiplying by n elsewhere, like here. And then if you play around with the divisor here, you'll end up with this. If you play around with the divisor, you'll end up with this. Okay, so that's the test statistic, which is a standard normal. That is true when the samples are large. Okay, then note that, because remember the Poisson distribution is a discrete distribution, so we need to include the continuity correction factor here. We need to include the continuity correction factor. So notice that it is easier to incorporate the continuity correction factor using the second version. It is easier when you include the correction factor using the second version, because you just add plus minus 0.5 on x. So you'll have something like that. But if you're using the first formula, you will have to take x bar plus minus 0.5 divided by n, just like we did in the case of a proportion. So it is easier to work with the second version. Okay. So example. So please note that about the correction factor, that when we are working with the first one. So let me just put it. So you're going to have x bar plus or minus 0.5 over n minus lambda naught divided by square root of lambda naught divided by this is not n naught. This is just n. This is not n naught. This is just n. I think there was a problem there. This is just n. Okay. So divided by n. Divided by n. And if you want to use the other version, you not divide by n. So you're going to have summation of the xi's. You just add or minus 0.5 minus n lambda naught divided by square root of n lambda naught. So that's how you incorporate the correction factor in both cases. Okay, so let's have an example. So example number 10, this is example number 10. And we are saying that in a 1-year investigation of claims frequencies for a particular category of motorists, the total number of claims made under 5,000 policies was 800. Assuming that the number of claims made by individual motorists has a Poisson distribution, test at the 1% level of significance whether the unknown average or mean claim frequency is less than 0.175. Okay, so solution, we are given, this is what we are given. We are given the number of trials in this case, n 5,000. We are also given summation of xi, the number of successes in this case, which is 800. And we are given the hypothetical mean frequency of the success outcome, the hypothetical population mean frequency of the success outcome, which is equal to 0.175. Then, of course, we're given alpha is 0.01. Okay, so we are testing the hypothesis that H naught, that lambda is 0.175 versus H1, that lambda. So what's the question here? Is less than. So we're testing whether this is less than 0.175, which is calling for a lower tail test. Now the test statistic. I want us to use X bar. So we shall use this test statistic, which is Z is equal to X bar minus mu naught, of course, plus the correction factor. Let me put it like this. This will be X bar plus correction factor, then minus lambda naught divided by the standard error, which is given by lambda naught divided by n. Then we take that. So our X bar, which is summation of xi over n, will be 800 divided by 5,000, 0.16. Okay, so this will be equal to 0.16, and our lambda naught is higher, so we're going to say plus 0.5 divided by n, and our n here is n is 5,000 minus our lambda naught, which is 0.175. Divide this by the square root. Divide this by the square root of 0.175 divided by 5,000. So let's simplify that. So when you simplify this, you'll get minus 2.5, let's say 116, something like that. 8516. Is that correct? Or there's a mistake?
19.
Sorry, yeah, there's a mistake somewhere. So this should be 19. So 19. So let's work with 19. Okay, so that's the calculated Z statistic. Then let's obtain the critical values of Z. The critical values. So remember, we are dealing with this. We have we are doing an upper tail test. Is it upper or lower? Lower tail test, sorry. So we're doing a lower tail test. Have critical region, which is alpha is 1%. And what is the critical value? You can quickly get it from R. So you can obtain the critical value using the R code. You can use the R code. If you don't want to use the tables, you can use the R code. The critical value is you have 0.01, because that gives you the cumulative probabilities all the way from minus infinity up to to a certain value here, which will so that the cumulative probability is 1%. So in this case, if you do the R code, you will get minus 2 point approximately like that. So here we have minus 2.33. And now we compare these two values. this one, and this one. And then we make our conclusion. So we notice that the calculated statistic falls in the rejection region. So this guy is here, minus 2.519. It is in the rejection region, falls in the rejection region. Thus, we have sufficient evidence to reject H naught, that lambda is 0.175, in favor of H1, that lambda is less than 0.175 at the 1% level of significance. At the 1% level of significance. Therefore, so the conclusion is that it is reasonable to conclude that the true claim frequency is less than 0.175. So it is reasonable to conclude that the true claim frequency is less than 0.175. Alternatively, we can also use p-values. And in this case, we'll be looking at the probability that Z is less than the minus 2.519. Minus 2.519. So this is the area that we are looking for. Is a p-value, minus 2.519. So you'll use the R code. P norm, and you have minus 2.519. That will give you the cumulative probabilities up to this point. Okay, and if you do it correctly, you'll get the answer is 0.005891 something, which is clearly a very small p-value. And a small p-value means that we reject the null hypothesis. And we'll end up with the same conclusion. So exercise, you try this at home. So the exercise says that a random sample of 500 policies of a particular kind revealed a total of 116 claims during the last year. You are asked to test the null hypothesis that lambda is equal to 0.18 versus H1, that lambda is greater than 0.18, where lambda is the is the annual claims frequency, where lambda is the annual claim frequency. So that marks the end of today's class. Any question? So from next week, we are starting with 2 sample tests. We shall repeat what we've done, but now using 2 samples. Any question?